Hello, in this tutorial I'm going to show how to train models in parallel using Pandas UDF with PySpark. So let's say you have thousands of categories or even hundreds of thousands of categories, and you want to train a model per category. You can use scikit-learn and train your models sequentially, but that could take so long. However, with the help of Pandas UDF, you can parallelize the same scikit-learn code and significantly shorten the time that it takes to train your models. So this tutorial assumes you have at least a basic knowledge about PySpark. At least you are able to create your own schema, and you know how to train models with scikit-learn. So here I'm importing a couple of functions, model training, multiple model training with gradient boosting classifier and random forest classifier, and we are going to perform cross validation using randomized search CV. So I'm importing randomized search CV, and also we are going to pre-process the data using standard scaler, and I will pipe all of them using pipeline. I'm just importing these packages and to show the capability that you can parallelize any complex function within using Pandas UDF with PySpark. As far as your function, as far as it is able to run with Python, and if you correctly define your schema, any kind of complex function you can run it in PySpark. So I want to return one very big thing here is when you use Pandas UDF in PySpark to parallelize your Python code, you have to make sure that it returns a data frame. So in this case, I want to return accuracy score, precision score, recall score, and area under the curve. So I'm importing these functions from metrics, these ones I'm importing from PySpark.sql.types, different data types. They will help me, as you will see later, they help me to define my schema. And finally, I'm importing here Pandas UDF and the Pandas UDF type. And so first, we are creating dummy data, and our data we are using make classification functions that we imported. Let's assume we have 100 IDs, and each of them have 1,000 rows and 30 features. So let's assume we have 1,000 categories, and each category has 1,000 rows and 30 features, and finally, and also another column, a response column. And also here, as you can see, I'm just looping for ID in range 100, generate dummy data with two classes, and create a list of data frames, and just finally concatenating them here. So this code, what it gives me is, it gives me the dummy data that I want to use here. It gives me dummy data that has 100 IDs, with each ID having 1,000 rows and 30 features, and also a response. I'm also here, as you can see here, I'm also adding the ID column because we want to train different models per ID. Okay, so let's check our data. So this is my sample data. As you can see, I have from XO to x29. So these are my so these are my features from x0 to x29, and I have my response here. So this is classification problem, binary classification, and we have ID. So in the sample data that I am showing, ID is 0 because our ID ranges from 0 to 99, and each ID has 1000 records. So until we go up to row 1000, ID will be just ID 0. Okay, so we have that data that we generated, and let's check. Here I'm checking its shape, and it says it has 10,000 rows and 32 columns. 30 of them are features. There is a response column and an ID column, so we have 32 columns in total, and we have 100 rows, 100 IDs, each one of them with 1000 rows. So we have 10k. Okay, let me check. So here I have 100 IDs, each one of them with 100 rows. So each one of them with, oh, this is 100, not 1000. Okay, so each one of them with 100 rows. So 100 times 100 is, as you can see here, 10,000 records and 32 features. Most important thing when you parallelize your Python code, any kind of Python code, it should not necessarily be machine learning. Any kind of Python code in Spark is to define your schema the right way. And here in my case, I just want per ID, I want to return recall, precision, accuracy, and AUC. So this is how we define schema. So we have the struct type, and with the struct field, I define the data type and the column of each one of them. And once I define my schema, my columns are from x0 to x29, and rather than manually putting them, I'm just getting them from here by dropping. If I drop the ID and Y columns, then I will be left with the features, and my response is Y. So once I do this, my data, so in here, the dummy data that I have generated is a Pandas data frame, but my data should be in Spark data frame so that I can parallelize it with Spark. So I'm converting my Pandas data frame to Spark using spark.create data frame here. So we have a Spark data frame here, and if you check the count, it should give me the same number of rows as before. So now let's, for example, run gradient boosting classifier with Pandas UDF. So how do we do it? First, we write a function, and that function will be applied per group by in our Spark code. But with the Python function, we use a decorator, and the decorator should be like this: Pandas UDF, and we pass the schema name, like my schema is this one that I have defined here, and the rest of this Pandas UDF type is grouped map. So once we do like this, in here, this is just the normal train test split model training with cross validation using randomized search, CV, and 5-fold cross validation, and the scoring method that I am using is F1, as you can see here. So what it does is, for each group by, think of this function will be applied to each group by, and for each group by, it will return a data frame, and for every ID finally you will get all the data frames per ID concatenated. So here what I'm doing is, okay, this df input in my model results per ID, this df is, let me start maybe from the Spark side. So I have the final df Spark data frame, and I'm grouping it by ID and using apply and calling this function. So what it does is, we have data frames per ID. So that data frame per ID, that is a df here, that gets passed on to this function. So I'm getting the ID is the same, there is only one ID per group by per grouped data frame. And now I'm getting the features and the response, I mean the features here from X columns and the response, and dividing my data into training and testing using train test split, with 30% for testing and 70% for training. Now in my pipeline, I just to show the steps, I am using standard scalar and also gradient boosting classifier here. But you can include any kind of complex data transformations in your pipeline, and as far as you create your schema correctly, it doesn't Pandas, you can parallelize it with Pandas UDF. So here I have the parameter distribution for the hyperparameters for a GBM. So we have the number of estimators, maximum depth, maximum features, and so on. This is something that we get from the scikit-learn GBM gradient boosting ensemble models API. So I am creating this list here, and from that list I just want to use 100 of them. So it is going to randomly sample 100 of them, and here it fits a model. Then I get predictions. Then once I have y-pred here, I can get the accuracy, precision, and recall. And I want also to get area under the curve, and for area under the curve I need not classes but rather probability predictions. So that is why I'm using here the predict proba. I need probabilities, and then using that I'm getting the area under the curve. So finally I am creating, at the end, pay attention here, I'm creating a data frame. So this is a data frame that has one row. So there is ID. For that ID we have recall, precision, accuracy, and AUC. So when we pass this function to the group by in the Spark data frame, then for each ID this function will be applied and a data frame will be returned. So you will get all data frames concatenated back. And so, but if you want non-data frame model result objectives from your function, you can save them like to S3 or to your disk. You can include on any code. For example, if I want to save this GBM CV method model object, I can just save it here using, for example, using joblib in scikit-learn. I can save it. Okay, so if I do like this, you see here it took 7 minutes to run it, about 8 minutes, 7 minutes and 43 seconds, and I'm displaying sample results here. So as you can see here, I have ID 0, 1, 2, 3, 4, and so on. So the ID ranges from 0 to 99. And for every ID, it gives me the recall, precision, accuracy, and area under the curve, or AUC. Now let's do the same thing using standalone scikit-learn. Just run it sequentially, and it is the same code, the same Python code, and it took about 31 minutes. So like this is about 4 times slower than the Pandas UDF. And when you have large volume of data and powerful cluster, with more number of nodes and more computing power, the time that you can save by parallelizing your scikit-learn code is really significant. And this is also sample results from the scikit-learn way. Let's try the same thing with random forest. I mean, you can use any model. Now I don't need to explain the steps that I explained before. Just the only thing is the estimator, I changed it to random forest, and this parameter distribution for the hyperparameters also, they have to be the appropriate hyperparameters. And when I ran this here, it took 13 minutes with Pandas UDF, and whereas with scikit-learn, it took about 1 hour and 1 minute. It took about 61 minutes. So this is about 8 times slower. So the main pointers that we have to remember when we parallelize our scikit-learn code with Pandas UDF are here. So when you are running models per group or per ID, using Pandas UDF in PySpark can save you lots of time, and the amount of time that it will save you depend on how many distinct IDs you have and the distribution of the data per ID, how big your data is, and the compute power of your cluster and the number of nodes. And yeah, the other thing is, if you want to compare results from scikit-learn with results from Pandas UDF with Spark, yeah, you have to make sure you use random seed, and especially if you are using randomized search. Without random seed, you don't expect to get the same results, because from the parameter distribution, it is just taking a sample of the combination of the different parameter, hyperparameter space from the hyperparameters that you have provided. And also, your data should not be very skewed to only very few of the grouping field. Like if you have ID as a grouping field, and even if you have 100 IDs, if 98% of the data is, for example, in ID1, it is more or less like training in models sequentially. So if your data is skewed like that, then you may not get lots of benefit from parallelizing it. But if it is fairly distributed using Pandas UDF and parallelizing it with PySpark, really saves you time. And the other thing that I want to mention here that I learned from using this is in your function, the results, they should not be numpy arrays. If they are numpy arrays, like if you have a single value and if it is array type, then an error, and in that case the array, you have to change it to just float or to decimal. And also, if when you define schema, if you have more columns in your function in the data frame, if the function returns a data frame with more columns than what you have defined in your schema, it just returns an empty data frame. So you have to pay attention you have to make sure your schema here, the number of columns and the data type is exactly the same as what this function is supposed to return. Otherwise, parallelizing any Python code with PySpark really saves lots of time. It should not, as I said, it should not necessarily be only modeling. It can be optimization also, like nonlinear optimization, for example. It takes lots of time, and if you want to optimize per ID or something, then parallelizing it like this saves you lots of time. And I hope you get it useful, and let me know if you have any questions.